All right, welcome back. So I've turned off the selection sort and I've turned on my insertion sort algorithm, but it's blank for now. So we're going to write the missing code. Insertion sort behaves a lot differently than selection sort. So in an insertion sort, what's going to happen is we're going to look at just chunks of the array. Like the first time, we're only going to look at the first two numbers. We're going to ignore the last 8. So nothing would change in the first iteration amongst the last 8 numbers. All we would attempt to do is to sort the first 2 numbers in relation to each other. If we were going from least to greatest, then this 35 would need to be on the left of the 45. So what I would do is I would move the 45 right 1 index, move the 35 left 1 index, and then that portion of the array would be sorted. As we go along, we keep picking up more and more numbers. So for example, by the time I got to this 3, that number 3 is smaller than any number to its left. So all of the numbers to the left of that 3 would have to move right 1 index, and then we would insert the 3 into index 0. Okay, if we look at like this number, say 17, which is currently at index 7, that would actually end up being the second number within this array. So at that point, all of the numbers in indexes 1 through 6 would have to shift 1 index to the right, and then we would insert that 17 into index 1. Let's imagine we were writing that chunk of code that I was just describing. So what that would mean is I would take over this index 7. Let's call that like our insert index, okay? And let's just put 7 there kind of arbitrarily for right now. And then I'm also going to make another int. I'm going to call this my insert value. And this would hold on to that 17 in this example. So that would look like nums at index 7, the value that's currently in the array at that index. What I would then attempt to do is to start comparing that value to values to the left of it. So we could do that example in like a while loop. Is this insert value smaller than the number found 1 to the left of where it currently is? So take that insert index, 1 away from it. If the insert value is smaller than the number to its left, okay, so in this case, like the 17 is smaller than the 47, I'm going to move that 47 to the right to make room for the 17 to come to the left. So what that would mean is that nums at insert index, okay, will be replaced by nums at insert index -1, okay, the number to its left. At that point, what I'm going to do is I'm going to take that insert index value and decrement it by 1. So what that would mean is now I'm going to go to this value, 94, which is at index 5. Is 17 smaller than it? Yes. So the 94 would then have to move 1 to the right. We've automated that through a loop, so that would happen. This would keep happening. Well, in this example, it's a little strange. It would keep happening until it hit that 3, and then it would actually stop. Now, at this point, what I would want to do is, once I found out like where this process ended at, I would want to put that insert value into that value to take over that index. So it would look something like this: nums insert index equals the insert value. Okay. So if you noticed, like there were moments when we were going to have 2 of the same value. So there was a moment when I had 2 47s in the array. There was a moment when I had 2 94s in the array. But at that point, then the 17 would take over one of those 94s and we'd be back to our original state. Okay, and so let's see, we don't really know, I don't really know what's going to happen because we got random numbers popping up here, but let's just see if we can walk through one step of this insertion sort. So what happened here was this 4 was at index 7, and that's smaller than 26, smaller than 74, 93, 19, but it's not smaller than 3. So what happened was these 4 numbers here all shifted 1 index to the right, and then the 4 inserted itself. Now, this wasn't truly an insertion sort algorithm. This is just kind of one step of it. prior to me encountering that 4, the 3 would have moved all the way to the left in a true insertion sort, and then the 4 would have taken over index 1. Now we're going to try to make that happen through a second loop, okay? Remember I was saying earlier that like the basic premise of the insertion sort is the first time up, you actually only want to look at the first 2 numbers. Then you want to look at the first 3, then the first 4, and so on and so on. So what we're going to do is we're going to automate this process with a loop around the outside, okay? This loop is actually going to start at index 1. Why don't we start it at index 0 like typical? Well, the reason we start at index 1 as opposed to 0 is we want to make a comparison to the left. So if we started it at index 0, there wouldn't be any numbers to the left. So we start at index 1. That way we can set up one comparison to the left. Remember how we have this -1 comparison coming up here. We don't want to go out of bounds, okay? And so let's see. All right. Now, this number here is going to be index I, okay? So there's no more arbitrary like 7, just kind of random. First time up, that's index 1. It's going to look to the left, see index 0, maybe pull off a swap, maybe not. Then we're going to start at index 2 and keep looking to the left. There's one problem here. If we pick up the smallest number, which at some point we likely will, not every time, but that number is going to start going to the left and eventually get all the way to index 0. And as a result, if we got to index 0 and we tried to go one more index to the left, we'd go out of bounds. So what we'll do is we'll take advantage of the short circuit, and we'll say that this insert index has to be greater than 0 for us to proceed. If it's not greater than 0, we don't want to try looking to the left. So in other words, once insert index hits 0, don't attempt to look to the left again, okay? Let's see what happens. All right, so we have a completely sorted array. You'll notice again that the outside loop actually ran 9 times. It didn't run 10 times. We started with 2 numbers, and then 3, and then 4, and so on. So there really was no reason to start at index 0. Like I said, there wouldn't be a comparison to be made. Because of this while loop here, allowing us to skip past values that are already sorted in relation to each other, potentially this thing's going to really speed up faster than the selection sort. If you gave the insertion sort a fully sorted array, it would actually just make one pass across, and the while loop would never run, and it would know that it didn't need to do anything, and so it would actually run at runtime n as opposed to n squared. You don't really need to worry about runtimes too much. This is also a stable sort the way that I've written it here, because when I encounter values that are equal, that's going to shut down the while loop. Therefore, if I had multiple 10s in an array or something, they would stay in their original order. Or in this example, I had multiple 89s. So the 89 that was originally on the left stayed on the left into this product here. All right, that's the insertion sort. Again, hope you're doing well. Let me know if you have any questions.